Imagine a conspiracy theorist. They look at the random events, a car backfiring, a bird flying south, the price of tea in China, and they weave a complex, perfect story connecting them all. They can explain everything that has happened in the past perfectly. But if you ask them to predict what happens tomorrow, they fail miserably. This is exactly what happens when your AI model overfits. It becomes conspiracy theorist. It memorizes the noise and misses the truth. But here is the secret that textbook won't tell you. Sometimes to fix this, you don't need less complexity. You need to make your model so massive it breaks the laws of statistics. Today, we're going to learn why. What's up everyone? Welcome back to Sumantra Codes. I'm Sumantra. I have spent years deploying machine learning models from everything from fraud detection systems handling millions of transactions to computer vision models. And if there's one thing that keeps me up at night, it isn't will the code run? Is the model actually learning or is it just pretending? I have seen senior engineers burn hundreds of thousands of dollars in GPU credits training a model that looked like a genius in the notebook but acted like a toddler in production. It is a career-ending mistake if you don't catch it early. We are doing a definitive deep dive. We are moving beyond the basic definitions. We are going to deconstruct the bias-variance trade-off mathematically. We'll visualize the geometry of high-dimensional spaces, and we'll cover two modern phenomena that have completely rewritten the rules of deep learning: double descent and Grokking. If you're ready to stop training conspiracy theorists and start engineering intelligence, buckle up. Before we talk about failure, we have to define success. In traditional software engineering, success is Boolean. If I write function to add 2 plus 2 and it returns 4, it works. If I run it a million times, it returns 4 a million times. Machine learning is different. We don't want the model to memorize the inputs. We want to understand the rule behind the inputs. This is called generalization. Think of the entire universe of data for your problem. Let's say picture of cats. That is the data distribution. It is infinite. You can possibly collect every photo of a cat that have ever existed or will exist. So you take a sample. This is your training set. Your goal is to use this tiny sample to approximate function fx that maps an image to the cat label. If your model learns the structure of a cat, such as ears, whiskers, fur, it has generalized. It can see a cat it has never met before and identify it. If your model learns the specifics of your training sets, such as cats only sits on red sofas because all your training photos had red sofas, it has failed to generalize. This is why we strictly enforce the train validation test split. So the training set is like the textbooks the student studies, and validation test is like practice exam. We use this to tune the model, and the final exam is the test set. The model never sees this until the very end. Here is the golden rule of ML. We do not care about training error. I can write a Python dictionary that maps every single training input to its label. That model has 0% training error. It's perfect. But on the validation set, it will have 100% error because it hasn't learned a single pattern. We are looking for the gap, the difference between how well you do on the practice test versus the real world. The gap is where your career is made or broken. Let's start with the first way of thinking go wrong, which is underfitting. Imagine you're trying to predict the trajectory of a rocket. The physics of a rocket are complex. Gravity, drag, thrust curve, it's a non-linear problem. Now, imagine you try to model that rocket using a ruler. You draw a straight line. This is underfitting. The model is simply not smart enough to understand the data. In technical terms, we say this model has high bias. Why bias? Because the model has a very strong preconceived assumption about the world. A linear regression model assumes the world is linear. It says, I don't care how curvy your data is, I'm going to draw a straight line. It is biased towards linearity. Because of this strong bias, it ignores the evidence in your training data. So how how do you know if you're underfitting? It's actually very easy to spot. The first thing is you see is high training error. So your model can't even learn the example you gave it. And the second is high validation error, which is since it didn't learn the examples, it obviously can't predict new data. It's like trying to teach a toddler calculus. No matter how much data you show them, they lack the cognitive capacity, the architecture to grasp the concept. In deep learning, this happens when your network is too small. If you have a data set of 10 million images and you try to classify them using a neural network with only 10 neurons, you are going to underfit. You are trying to compress the complexity of the visual world into 10 numbers. It's impossible. So, what is the solution? The solution is you can increase the complexity or switch from a linear model to a nonlinear one. You can add parameters, which means adding more layer to your neural network, give it more brain cells. And finally, you can do feature engineering. If you're doing a linear regression on a curve, give the model x square as a feature, not just x. Now, the more dangerous villain, overfitting. This is our conspiracy theorist. You gave the model enough capacity to learn the curve, but you gave it too much capacity. Instead of seeing the smooth curve or the signal, it saw the tiny fluctuations in measurement or the noise and thought they were important. Mathematically, every data set is composed of two things. Y is equal to fx plus epsilon. Fx is the truth, the underlying pattern, and the epsilon is the noise, random error, sensor jitters, and bad labeling. An overfit model calculates a function f hat of x that includes epsilon. It treats the noise as a fact. We call this high variance. Why variance? Imagine I take your data set and split into two random halves, A and B. If I train a high variance model on set A, it will learn the specific noise of set A. If I train it on set B, it will learn the specific noise of set B. The two models will look completely different. The model varies widely depending on the specific subset of data it sees. It is unstable. This is the signature look of overfitting. First, the training error is near zero. It memorizes the answer. And the second, validation error is massive. It knows nothing. This is what happens when you train a massive ResNet 50 on a dataset of 50 images. The network has millions of parameters. It can't just assign one parameter to memorize each pixel of each image. It doesn't need to learn ears or whiskers. It just learns image number 1 is equal to cat. How do we fight this? We have three main weapons. First is more data. This is the brute force fix. If you have enough data, it becomes very hard for the model to memorize the noise because the noise cancels itself out. The signal becomes the only consistent thing. The second one is regularization. This is the elegant fix. We mathematically punish the model for being complex. So we have different kind of regularization. The first one is L1 or L2 regularization. We add penalty to the loss function based on the size of the weights. If the model tries to use massive weights to fit a weird outlier, we slap it on the wrist. The second one is dropout. In neural networks, we randomly turn off 50% of the neurons during each training step. This forces the network to be redundant. It can't rely on a single grandmother neuron to memorize a specific example. And the third strategy is early stopping. Watch the validation graph. The moment the validation error starts to creep up, kill the training. Stop the student before they start memorizing the typos in the textbook. This brings us to the fundamental theorem of machine learning, the bias-variance trade-off. Let's look at this graph. On the far left, we have a low complexity or a simple model. Here, bias is high, but variance is low. The error is high because we are underfitting. On the far right, we have an extreme complexity. Bias is low, the model is flexible, but the variance is high. The error is high because we are overfitting. So, the total error of your model can actually be decomposed into an equation. Total error is equal to bias square or a square of bias plus variance plus irreducible noise. Here is the tragedy of this equation. You usually cannot reduce both at the same time. If you make the model more complex to reduce bias, you increase variance. If you simplify the model to reduce variance, you increase bias. Your job as an engineer to find the Goldilocks zone, the bottom of the U-curve, the sweet spot where the model is complex enough to capture the signal, but simple enough to ignore the noise. For decades, This was the law. It was written in stone. We believed that if you kept adding parameters to a model, eventually you would cross the threshold and destroy its performance. But we were wrong. In the last few years, deep learning has broken this curve. We discovered that if you keep pushing past the point of overfitting, if you go absolutely crazy with complexity, something magical happens. This is called double descent. It was popularized by researcher at OpenAI in Belkin around 2019, and it explains why massive models like GPT-5 works. Here is what we are looking at. The first thing is the classical regime. The first U. This is what we talked about. As the model gets bigger, it overfits. The second is the critical point. This is the peak of the error. This happens when the number of parameters in your model is roughly equal to number of data points. Capital N is almost equal to capital P. At this point, the model is forcing itself to memorize the data, but it has to contort itself wildly to do it. It is a jagged, messy fit. But then you keep adding parameters. You make the model huge, 10 times more parameters than data points. Suddenly, the test error drops again. This is modern interpolation regime. Why does this happen? Think of it this way. If I ask you to draw a curve through 3 dots and I give you a complex polynomial, there are infinite ways to draw that line. When the model is massive, it has so many options of parameter that it doesn't need to be jagged to fit the data. It can find a smooth solution that hits every training point perfectly without fluctuating wildly in between them. In this regime, the model effectively acts like a nearest neighbor search. It interpolates smoothly between the training examples. This is why we can train large language models with trillions of parameters. According to the old bias-variance theory, they should overfit massively. But because they are so big, they enter the second descent and generalize beautifully. So the takeaway is, don't get stuck in the middle. The worst place to be is at the interpolation threshold, and either keep your model simple, such as classical machine learning, or make it absolutely massive like modern deep learning. The middle ground is where the error lives. If double descent wasn't weird enough, let me introduce you to Grokking. This is a phenomena discovered very recently in 2021 or 22. Usually, if your training accuracy is 100% and your validation is 50%, you stop. You assume the model has overfit and failed. But with Grokking, we see something bizarre. The model memorizes the training data quickly. It cheats. It builds a lookup table inside its weights. But if you keep training, and I mean keep training for a long time after the loss has flatlined, the model undergoes a phase transition. Suddenly, the validation accuracy spikes. The model groks the solution. It switches from memorization to algorithm. Why? Turn out generalized solution or the real math are more efficient than memorization in terms of weight magnitude. If you use weight decay or regularization, the model is under constant pressure to make its weight smaller. So, the memorization circuit requires complex messy weights to handle every exceptions, and the general circuits often simple, elegant math. Over time, the regularization pressure forces the model to abandon the messy memorization circuit and discover the clean general circuit. It is like the model initially cheats on the test, but the teachers keep staring at. So eventually, it sighs and actually learns the math because it's less effort than maintaining that cheat sheet. This teaches us patience. In the era of transformers and algorithmic tasks, sometimes overfitting is just a temporary state before enlightenment. We have covered everything from the basics of bias to the bleeding edge of meta learning. Let's condense this into 3 things you need to take back to your engineering team. First, trust the validation set, not the training set, which means it doesn't matter if your model has 99.9% accuracy in the notebook. If it drops 60% on the validation set, you have a memorization machine, not an AI. Treat the training loss as vanity metrics. Second, respect the trade-off, but know the regime. So, for small data, the simple models like random forest or linear regression, the bias-variance trade-off is law. Don't make the model too complex. But if you are in the realm of deep learning, remember double descent. Sometimes the solution to overfitting isn't the making the model smaller. It's making it bigger and feeding it more data. And the third, patience is a hyperparameter, which means if you are training on complex algorithmic tasks, don't kill the run just because validation looks flat. Grokking proves that generalization can happen long after memorization. So I want to hear it from you. Have you ever experienced the double descent in your own work? Or have you killed a model early that might have been about to crock the solution? Let me know in the comments below. I want to see your war stories. My name is Sumantra and this is Sumantra Codes, and keep engineering intelligence.